Okay, so our speaker from GTP is Corinna Ulcigrai. We're very happy to have her here today. She's been professor at the University of Zurich since the last few years, and she moved here from Bristol.
Okay, so thanks a lot. I would like to present mostly paper which was recently published just a few months ago on Invenciones Matematicae, and it's a joint work with Kanigowski and Lemancic. And en passant, I will also mention related work on the Journal of the European Mathematical Society, also with Adam Kanigowski and Joanna Kuaga-Pshimos. So the topic is, as you see from the title, shearing and disjointness in locally Hamiltonian flows. So let me start with what are they. So we take a closed surface and we look at the motion of a point described locally by Hamiltonian equation. And if you want globally, you are assigning closed one form on a symplectic structure. And this one form in suitable coordinates is the differential of your Hamiltonian. So this type of flows have a physical motivation. So they were studied since the 90s, and Sergei Novikov used them as a model for the motion of electrons in a metal under a magnetic field. So the surface is actually the Fermi energy level surface for the metal. This is a periodic surface, but when you quotient it, you get the compact surface where the locally Hamiltonian flow lives. And I will be mostly talking about chaotic features or chaotic properties of these locally Hamiltonian flows. And the interest in those started with a conjecture by Vladimir Arnold, also in the 90s. So Arnold specifically looked at the torus, the genus 1 case, and conjectured that these flows are mixing, so have decay of correlations. So if you take two smooth observables, and compose one with the flow, it decouples, F composed with Φt decouples from G. And there was a lot of research on this mixing, and actually I was heavily involved in the higher genus case, but this happened more or less 10 years ago. I just mentioned en passant a result by Ravotti, which was also a postdoc in SwissMap, and he recently proved that the decay of correlation is actually very slow, so it's not exponential as in many systems, but it's even super-polynomial. It decays like a log, the power of log. And there is a geometric mechanism which helps understanding decay of correlation, so-called shearing. So you can study how nearby points evolve, and they have different deceleration rates, and this creates shearing. So some transverse arcs are sheared in the direction of the flow. So this mechanism will come back in a second. And so a question which was open for at least the past 10 years is, can we go beyond mixing? So can we prove something more about the spectral or the rigidity and disjointness properties of these flows? And we'll answer today two of these deeper questions. So the hope would have been to use shearing, but somehow there was no idea how to attack these deeper questions. And there is an example in the mathematical literature which is very celebrated and famous, and it's in the work of Marina Ratner. So Marina Ratner, and also then many Fields medalists like Margulis and Lindenstrauss, proved some quite amazing rigidity results in on Lie groups, in homogeneous dynamics. So here the setup would be quotients of a Lie group by a lattice. And the key tool in Ratner's work is a shearing property, but it's a very precise quantitative form of shearing, and we call it today Ratner property. So the hope in the community was that one could maybe hope to prove Ratner's properties in other contexts, and it's been so successful in homogeneous dynamics that maybe if we could prove it, for example, for locally Hamiltonian flows which display shearing, this could lead a lot of consequences. So unfortunately, there is a key difficulty, and this is due to singularities. So in these flows, there are singular points, for example, saddle points, and singularities introduce discontinuities, and they make the control of shearing difficult. So at singularities, you lose control of shearing. So the first result I will mention, I have 2 more slides. So one is about the GEMS paper with Kanigowski Kuaga. So we could prove finally that locally Hamiltonian flows in the right assumptions typically don't have exactly the Ratner property, but they have a variant of the Ratner property, which can be used in the same way that Ratner did. And the variant was introduced actually by Fayyad and Kanigowski for the genus 1 case, and we proved it in any genus here. And as a corollary of this result, for example, we already can study higher decay, multiple decay of correlations. So if you have mixing of all orders, it's called. So if you don't have 2 but n observables and you compose them with the flow, you look at the multi-correlation. Multi-correlation also converge to what they should. And this variant of the Ratner property is also at the base of the latest result. So the paper with Kanigowski and Lemanchik. So this paper is about disjointness. So let me tell you what is disjointness. So first of all, if the result is for Arnold flows. So for the case of genus 1, I don't know if I said, but genus 1 is called Arnold flow in honor of Arnold and his conjecture. And if I look at the flow and I rescale it linearly, so I take not the flow, but the flow at times kappa t, I just do a time linear rescaling of time. What we prove is that the rescaled flow is disjoint from the original flow. So this disjointness is a property which Furstenberg introduced in the 70s, and it involves the notion of joinings, which I will not define. But essentially, it says that 2 flows are related to each other. And I want to stress that this is very surprising. So this property is typical for very chaotic systems, like if you have a Gaussian flow or Bernoulli systems, then you have disjointness. But our systems, these surface flows, are entropy 0. They are very little, very deterministic and very little chaotic. So it's kind of surprising. And this disjointness property came into play into the proof, into a conjecture of Sarnak called Möbius orthogonality or Möbius disjointness. So it's a number theory conjecture on the properties of the Möbius function, counting distinct primes factors. Essentially, once you have this jointness of rescalings, you automatically have the Möbius conjecture. So this in particular gives the Möbius conjecture for Arnold flows. And I think it's intrinsically surprising or interesting, but our proof is based on the Ratner property, on our variant of the Ratner property. So we have a new criterion for disjointness which exploits this geometric shearing. And it has already found several other applications. So there are results for von Neumann flows and Heisenberg-knit flows that use our disjointness criterion. And of course, what I'm currently working on is how to extend this in higher genus. So this is for genus 1, and it already was well received, but somehow I really want to tackle the higher genus case. And I think we finally are close to get to have it. We have already the switchable Ratner property, and now we are technically working on settling the higher genus. And again, there are a lot of technical part, which I will not go into, which exploits dynamics in moduli space of surfaces and Diophantine conditions which come from Teichmuller dynamics and are exploited to prove implicitly this type of results. Okay, I will stop here and I thank you for your attention. Okay. So.
Well, thanks a lot. Yeah, could you maybe say a couple of words? I understand that the proofs are, I guess, are very technical and very complicated. Maybe the format is not kind of suitable to present them, but what are the what are the ideas? So you want to control this shearing, and then what's the key idea? How can you handle it?
Yeah. So but I wonder, so first of all, there are two separate parts. So one part is in some sense in what I was calling this disjointness criterion. So how to exploit shearing to prove disjointness, and this is one part. And then, as you say, the second part is to apply this criterion. Is you need, for example, actually we don't only do it for Arnold flow, we also study time changes of horocycle flows, and we have other type of disjointness results which we use the same new criterion. But so another part is indeed about locally Hamiltonian flows, how to implement it. So how to get the right form of shearing. So if maybe I will focus on the second, because maybe it's where there is more also geometry of surfaces. And so in this part you need, okay, as I said, we already knew shearing and what was used for mixing, and now we have to a refined form that more quantitative. And what you need is kind of sophisticated conditions, which not every flow will have such a strong form of shearing. Only a typical means here full measure in the space of locally Hamiltonian flows. And to characterize, we have an explicit, we call it Diophantine condition, because like in the case of actually it is in this case of genus 1. So you have to do a Diophantine condition which guarantees that you have the right shearing property. And maybe I will say something. So in this case, it's like really Diophantine condition. When you instead want to, for example, prove the switchable Rathern property in higher genus, like we were doing in the GEMS paper, or when you want to extend this result to higher genus, you need to work in the moduli space of surfaces, moduli space of abelian differentials. Those are surfaces with a certain geometric structure. And you need to look at the geodesic flow there and characterize geodesics which have certain return properties on compact sets. So the spirit is to kind of prove that these properties have full measure by using ergodicity or chaotic features of the Muller geodesic flow on the space, on the moduli space. So there is this interplay between dynamics and geometry and the physical application. So does this, I don't know, I don't want to go into too much.
Corinna, I also have a question.
Yes.
Does anyone ever work on higher dimensional, like the K3 surface? That's maybe the analog of the torus, like a symplectic fourfold.
Good question, but no, I'm not aware. So, but which type of, no, the only,
the whole subject, you can talk about the, I mean.
No, there is connection between K3 surfaces and like Muller dynamics. There are two people who are looking into that, and it's Philip Simeon. He was a student of Ales Eskin, and together with Valentino Tosatti, who does more the analysis part, but they are studying more, they're using Lyapunov exponents, the concept of Lyapunov exponents in Muller dynamics, and so they are kind of to use ideas from
behind me. That's a K3.
Oh, wow. Yeah, so this is the only people that I know are working on, but it's true that there are connections possibly can be drawn between Muller dynamics and, but it depends on which specific questions you want to address, and yeah.